Good day, everyone. Welcome to lecture number 30 of Theory of Computation. And in this particular lecture, we will be discussing about the power of Turing machines. How strong are Turing machines? So let's first see about the regular language. Okay. So for our regular language, or we can say regular language means DFA. So regular languages, they are as powerful as computers with finite memory. With finite memory. Okay, so we have already discussed this. So if we have a computer, so this is our computer. Okay, and this computer has a memory, and this memory is finite. Okay, then I am saying here the power of this particular computer is same as power of regular language, or we can say power of DFAs. What is a DFA? DFA is basically a mathematical computational model. So whatever problems can be solved by this DFA, the same problems can be solved by a computer with finite memory. Okay, so our regular language or our DFAs are as powerful as computers with finite memory. Okay, and we know the computers with finite memory are our real computers. So what is a real computer? We know the actual computer that we are using currently, those are computers with finite memory. Finite memory means they have a finite RAM, random access memory, and they have finite disk space. Okay, so our real computers are as powerful as regular language, or we can say as powerful as DFAs. Okay, now in these computers, in these real computers, when we increase their memory, increase the, or we can say increase the size of their memory. Okay, when we increase their memory size, their power also increases. Okay, so with the increase in memory size, power also increases. For example, currently you may be seeing there are computers. Let's suppose there are some computers with, let's say, 8 GB of memory. Main memory I am speaking about, and there are other computers with 128 GB of main memory, and this computer is powerful as computer this particular computer. Okay, so we can say with the increase in memory size, power of computers increase. That is their, we can say the capability of solving the problems increases. Okay, so from this, we can say that from the real computer, we can have an idealized computer, or we can say what is the maximum size of memory that we can achieve. So in future, the maximum size of memory can be infinite. Infinite means extremely large amount of memory. So this is the idealized size of memory. Idealized size of memory. Okay, so that means this kind of computer, So this computer with infinite memory. Okay, computer with infinite memory. So this computer will be the most powerful computer. Why most powerful computer? Because it has infinite memory. And this is the only possible, or we can say the highest possible powerful computer that we can design in the future. We cannot have a computer that is more powerful than this particular computer. And this computer is also called an idealized computer. Okay, a computer with infinite memory. And this particular computer has infinite RAM and infinite disk space. Okay, this particular computer. And any problem in the world that can be solved, that cannot be solved by this particular computer, means that particular problem cannot be solved. So if we have a problem, if we have some problem, let's say problem 1, if it is solved by, if it is not solved by idealized computer, what does that mean? If it is not solved by an idealized computer, it means we cannot solve problem 1. Okay, so that means that particular problem cannot be solved. So any problem that has a solution on an idealized computer, that means that particular problem can be solved. And any problem that cannot be solved by an idealized computer means there is no possible computational model that can solve this problem. Okay, and these computers are our futuristic computers. So this is a futuristic computer. Okay, so a computer with infinite memory. So this is the possible, this is the, we can say, the most powerful computer that we can design. We cannot design any computer that is more powerful than this particular computer, this idealized computer. So that means all the problems in the world, or we can say the problems that can be solved, or we can say the problems for which there exists a solution, or we can say the problem solved by any feasible computing machine. That means those problems can be solved by this idealized computer. And the problems that are outside this particular space, so that means those problems cannot be solved by any computer, not in the future, not in the present, not in the past. Okay, so what I am saying here, so I have said that we have computers, we have our computers. Okay, these are our real computers. They have finite memory. Fine. So these computers, these correspond to DFAs. or we can say any problem that can be solved by a DFA, any problem for which there exists a DFA, that means that problem can be solved by a real computer. And with increase in memory, what happens? Computational power increases. Computational power increases. Okay. And with further increase in power, that means with ideal memory. Ideal memory. So what is the ideal memory? Ideal memory means infinite memory. We will reach to a computer which is called an idealized computer. And this idealized computer will be a most powerful computer that we can design. And this can be designed in the future if possible. So it is not necessary that it is possible to design an idealized computer. That means a computer with infinite memory, but we are saying that if possible, that particular computer will be the most powerful computer. And we will claim that this idealized computer is equivalent to our Turing machines. What does that mean? It means that a problem that can be solved by a Turing machine, that means that particular problem can be solved by some computer. Some computer. That may be an idealized computer or any computer below this. Okay. So what I am saying that Turing machines are equivalent to idealized computers. So that means the problems solved by Turing machines are solved by idealized computer, or we can say they are solved by some computer. So that computer may be the past computer in the past, or the present computer, or the computer that we can design in the future. Okay. However, if there is some problem that cannot be solved by Turing machine, problem not solved by Turing machine. What does that mean? If there is some problem that cannot be solved by a Turing machine, it means that the same problem cannot be solved by any computer. Any computer means the computer in the past, the computer in the present, or the computer that we can design in the future. Okay, so that means no computer can solve that particular problem which cannot be solved by a Turing machine. So what I am saying here, I am saying here that Turing machines are equivalent to idealized computers. So this is my claim that Turing machines are equivalent to idealized computers. So this is our claim, but we have to prove this claim. So we have to prove it. Okay. So how will we prove it? This particular claim that Turing machines are equivalent to idealized computers. First thing we will prove that any problem, or we can say the problem, the first thing that I want to prove is that idealized computers can simulate Turing machines. So this is the first thing that I will prove, that idealized computers can simulate Turing machines. What does that mean? It means anything that can be done with a Turing machine can also be done with a computer with infinite memory. Okay, so that will be the first thing. The second thing that I will prove is that Turing machines can simulate idealized computers. Okay. So what does that mean? Turing machines can simulate idealized computers. It means that anything that can be done with an idealized computer can also be done with a Turing machine. So if I am able to prove these two things, then I can say that Turing machines and idealized computers are equivalent to each other. So let's prove these two things. Idealized computers can simulate Turing machines. So this is our claim one. This is our claim two. So we will prove both these claims. Okay. So let me write the claim one first. What is claim one? Claim one is that idealized computers can simulate Turing machines. So I won't be discussing it in detail, but I will give an idea how idealized computers can simulate Turing machines. So what does that mean? It means anything that can be done with a Turing machine can also be done with a computer with unbounded memory. Unbounded memory means infinite memory. With unbounded memory. Okay. So let's see how we can do it. How anything that can be done with a Turing machine can also be done with a computer with unbounded memory. So what is Turing machine doing? So let's see what is Turing machine doing. So we have a Turing machine. It has states. Okay. And it has an input. Turing machine takes an input, takes symbol from the input, changes state, and also moves left or right. So these are the things. So what we have to store for a Turing machine? So for a Turing machine, any Turing machine, we have to store its transitions. What are its transitions? Transitions means we have to store the transition table. Okay. Transition table means that if there is a current state input, what will be a new state and where we have to grow, left or right. Okay. So for any Turing machine at any point of time, at any point of time, we should know the following details. We should know what is its current state. Okay. Plus, we should also know what is there on the input tape. Okay. What is there on the input tape? So this is the input tape. And there may be data on the input tape. Let's suppose A, B, B, A. Plus, we should also know where is the tape head. Okay. So let's suppose tape head is here. So these things at any point of time, we should know these things. So how will we have these things? We can store these things using a single string. So what will be the string? We will first write whatever is there on the left of this tape head. So what is there on the left of tape head? AA. Then after AA, we will write current state. What is current state? Let's suppose current state is Q1. So it will be Q1. And whatever is on the right of this tape head, or we can say starting from the tape head. So it is B, B, A. So at any point of time, we have to store this. So this is also called the snapshot of a Turing machine. Snapshot of a Turing machine. So these are the details we should know. Now let's suppose our Turing machine is right in this snapshot. What will be the next snapshot? Next snapshot is current state is Q1. What is the input? Input will be B. So input is B. Now we have current state Q1, input is B. Now using this transition table, we will find out what is the new state. Let's suppose new state is Q2. Okay, and it is moving, let's say left. Left means it will go here, and it will rewrite new thing as A. So here it is writing A. So now the tape head is here. So from this snapshot, we will get a new snapshot. The new snapshot will be A. A means whatever is on the left of tape head. Then new state, what is the state? Current state Q2, and whatever is on the right side. So right side is A, B. This is another snapshot. So how many snapshots are possible? There are infinite snapshots. Infinite snapshots. But we don't have to store the infinite snapshots. We have to only store a single snapshot. Okay. So if we have a computer with unbounded memory, then we can store all the details of a Turing machine. What are the details? The details are transition table. Transition table can be infinite. It can have an infinite size. Okay. Plus, we can store the current state, and we can store the all possible snapshots. So all possible snapshots are also infinite. So we can store all these details about a Turing machine in the unbounded memory of the computer. Okay, all these details. So we can store all these details in the unbounded memory of a computer. Now this Turing machine, what it was doing, it was checking the input, and then from that input, it was moving to a new state. Now, the same thing we can do with this unbounded memory. We have stored all the information in this unbounded memory. Now we can take the initial snapshot. What will be the initial snapshot? The initial snapshot will be Q0 and the input string. So we will start from this initial snapshot, and we know this initial snapshot is also stored in the unbounded memory. Now from this initial snapshot, and using this transition table that is also stored in the unbounded memory, we can make transitions one after the another. So whatever transitions were there in the Turing machines, those transitions can also be performed using the information that is stored in this unbounded memory. So that means anything that can be done with a Turing machine can also be done with a computer with unbounded memory. But we have to store these details in that unbounded memory. So I have not given you the complete proof, but I have tried to make it clear how we can do anything that was done by a Turing machine using a computer with unbounded memory. only detail is that we have to store in this computer with unbounded memory is the transition table, current state, and the snapshots of the Turing machines. Then from these details, we can perform all the operations that can be performed using a Turing machine. So we can say idealized computers can simulate Turing machines. Okay. So I hope I have helped you to understand this particular concept, or we can say the proof of our claim 1. Okay. Now let's move to claim 2. So what is our claim 2nd? The second claim is, what is the second claim? Second claim is Turing machines can simulate idealized computers. Okay. So that means anything that can be done with an idealized computer can be done with a Turing machine. Okay, so we have to see it. So what is an idealized computer? We know an idealized computer is a computer with finite control plus infinite memory. Finite control plus infinite memory. And any idealized computer, or we can say any computer, can perform operations. So it can perform operations by using some basic operations. So what are the basic operations? The basic operations are arithmetic operations, or we can say array operations. What are the array operations? For example, array operations are sorting an array, concatenating two arrays, or we can say concatenating two lists, or reversing a list. Those are array operations. And the other operations are memory, read and write operations. Read and write operations. So these are the operations. Using these operations, idealized computer can perform any operation in the world, any possible operation in the world. We will see that the same operations can be performed by a Turing machine as well. So what is our Turing machine? The Turing machine also has a finite control, and it also has infinite memory. Infinite memory. So that means the resources of the Turing machine are same as resources of a idealized computer. Now coming to the operations, we know we have already discussed a Turing machine for incrementing. We have also discussed a Turing machine for decrementing. So using that particular Turing machine, we can perform any arithmetic operation. So that means arithmetic operations can be performed by Turing machines. Now coming to an array operations. Array operations can also be performed by a Turing machine. For example, if we have an array, let's suppose we have the following numbers in the array. Let's say A, B, A, A. This is our array. And we want to reverse this array. Reverse this array means the final result should be A, A, B, A. So can we perform this operation using a Turing machine? Yes, we can perform it. So for example, I won't give a complete detail of the Turing machine, but I will help you to understand how this can be done. Let's say this is the input array here, A, B, A, A. Okay, this is on the memory of this Turing machine. Now we have to reverse this. So how will we reverse this? We will first go here, A. Okay. So what we are going to do, we will go to the end. Go to the end. So this is the infinite tape. So all the others are blank. So we will go to the end first. So what is at the end? A. So we will write this A here. Then we will move one place to the next. What is there? A. Go here, put A. Move another place here. What is here? B. Right here B. Move another place here. What is here? A. Move another place here. but here we have now blank. Blank means ended. So the reverse of this particular array is stored here. So I won't be helping you to design this Turing machine because we have already designed many Turing machines. So it is your job to design a Turing machine, full-fledged Turing machine for reversing the string. So you can store the same string at some other location on the input tape, but we should get a reverse of this particular string. Okay. So that means array operations can also be performed by a Turing machine, and these memory read and write operations, because Turing machine is already doing memory read, reading from this input tape and also writing some new things on this input tape. So memory read and write operations can also be performed by a Turing machine. So all the operations that are performed by an idealized computer can be performed by our Turing machine as well. So we can say Turing machines can simulate idealized computers as well. So from these two claims, we concluded. So what is our conclusion? The conclusion is that Turing machines are equivalent to idealized computers. So this is the power of Turing machines. Okay. So what does that mean? It means from this we can say that it means any problem solved by any computer in the world, any computer. This computer may be in the future as well, for in the future as well. Any problem solved by any computer can be solved by a Turing machine, and vice versa. Or we can say any problem that cannot be solved by a Turing machine, any problem that cannot be solved by a Turing machine cannot be solved by any computing device. So there is one exception here, that is when we discuss about the quantum computers, but that is out of scope of this particular course. So you will be discussing about that in quantum computers. Okay. So any problem that cannot be solved by a Turing machine cannot be solved by any computing device. Or we can also write it that what can be solved, or we can say a problem whose solution exists algorithmically it implies Turing machine can solve that problem. Or we can also write that every effective model of computation is equivalent or weaker than a Turing machine. Okay. So, or we can say any problem for which there exists a solution, that means that problem can be solved by a Turing machine. Or we can say any problem for which there does not exist any solution, that means that problem cannot be solved by a Turing machine. Okay, fine. So these statements, the statements that I have written here, these are different ways of saying the same thing, and these statements form the church-turing thesis. So church-turing thesis is saying that if a solution does not exist for a problem, that means that problem cannot be solved by any Turing machine. Or we can say a problem that cannot be solved by a Turing machine, that means that problem cannot be solved. Okay, so from this we have also reached to a conclusion that if we have problems, so these are our problems. Problems means those problems for which there exists a solution. Or we can say the problems which can be solved by some feasible computing machine. Solved by some machine. So these problems, or we can say these languages, because language is also a problem. Okay, these languages are also called or we can say these problems are those problems which are solved by Turing machines. And in these languages, in these problems, there is a subset which are called regular problems, or we can say regular languages. And there is another subset of these problems which is context-free languages. So this is a set. So this set includes all problems for which there exists a solution, or we can say it includes all those languages for which there exists a recognizer. Recognizer means there is some computing device that accepts these languages, and these languages are all called the languages of a Turing machine. And subset of these languages are regular languages and context-free languages. And we have to discuss what is a language of a Turing machine, and we have to also discuss, is there any language outside this, or we can say, is there any problem outside this? Any problem outside this means that is there any problem that cannot be solved? Or we can say any problem that cannot be solved by a Turing machine. Or we can say any language that cannot be recognized by a Turing machine. So we have to answer these questions. So first thing we have to understand, what is a language of a Turing machine, and is there any problem that cannot be solved by a Turing machine, or we can say any language that cannot be recognized by a Turing machine. So these things we will be discussing in our next lecture, that is lecture number 30. So before ending this lecture, I am giving you here some of the problems that you should understand. So this is your homework. So you should design Turing machines for following. So first is reversing a list, or we can say reversing a string. So the string may be formed only of A and B. Second, concatenating two strings. Concatenating two strings. And the third is finding maximum and minimum in an array. Minimum in an array. So you have to design Turing machines for these problems. Okay, so let's meet in the lecture number 31, where we will be discussing about the language of a Turing machine. So till then, goodbye.